I would like to take the unit of block elements. Here, before learning of block elements, first we should know the very clear the definitions of block elements. Not only the block elements, but also S, P, D also. Within 1 minute, we are able to write all kinds of definitions of all the blocks which are present in the periodic table. Example, if you want to write the definition of a block elements, you can write very simple. When the differentiating electron is entering into the n-2 into f orbitals, when the differentiating electron is enters into the n-2 into f orbitals, that elements are called as a block elements. It means simply we can say whenever the differentiating electron is entering into the f orbitals or f sublevel that are known to be a block elements. If that differentiating electron is enters into the s orbital, that kind of the elements are called as S block elements. If this differentiating electron is enters into the d orbitals or d sublevel, then automatically we can see the definition of that elements are called as d block elements. In the same way, to the p block also we can give the same kind of definition, because the last electron or differentiating electron is entering into the p orbitals. But now today we are going to learn about the a block elements only. Before learning of a block elements, first you observe it here. This is the outline diagram of periodic table. Here this is the main body. Under the main body of periodic table, the block elements are kept here itself only, below the main body of periodic table. Here these block elements are arranged in two horizontal rows. This is the first horizontal row, this is the second horizontal row. First horizontal row is nothing but lanthanides, and the second horizontal row elements are called as actinides. Generally, lanthanides are starting from 58 atomic number elements, that is cerium to 71 atomic number element, that is lutetium. From cerium to lutetium, there are 14 metals are there. That elements are called as lanthanides. But whereas when you are taking from atomic number 90, that is thorium element, from thorium to lawrencium, it means 90 atomic number to 103 elements. Here also there are 14 metals are there that are kept in the actinides. The combination of lanthanides and actinides are called as a block elements. Here normally they are asking sometimes regarding this question. Here in case of cerium to lutetium or in case of lanthanides, the differentiating electron is entering into the 4f orbitals. Therefore, the lanthanides also called as 4f series metals or 4f series elements. When the differentiating electron is entering into the 5f orbitals or 5f sublevel, that are known as actinides or 5f series elements or 5f series elements. These are the 4f series elements, because the differentiating electron is entering into the 4f orbital. These are called as 5f series elements because the differentiating electron is entering into the 5f orbitals. And here sometimes in medical and engineering and IIT mains and advanced examinations they are asking, even the period number is also here. Lanthanides are present in the 6th period of periodic table, and actinides are present in 7th period of periodic table. Remember, lanthanides are present in 6th period, actinides are present in 7th period. Here we should know one important word, that is the differences between, very small differences that are 100% useful to get a complete an idea of the block elements here. Lanthanides and actinides. Simply you can write it here, the lanthanides are 4F series elements, these are the 5F series elements, and these are present in 6th period, whereas actinides are present in the 7th period. You know, you might have seen, that is about lanthanides. Lanthanides also called as rare earth metals. These are rare earth metals, as their occurrence is very rare in the earth crust. Therefore, they are called as rare earth metals. But whereas actinides are called as, there are many names are there, synthetic elements or synthetic metals, or one more word is also there, that is artificial metals, artificial metals, or man-made metals, man-made metals, synthetic metals, artificial metals, man-made metals, and one more word is also there, that is transuranic metals, transuranic metals. These are the different names of the actinides. Once again you observe it here, 4F series, 5F series, 6th period elements, 7th period elements, rare earth metals, man-made elements, because almost all these elements are made by the man only. They are the artificial elements, so that they are called as artificial or synthetic or trans. I think almost many of the metals are made by the nuclear transmutation reactions only. Therefore, they are called as artificial metals. After that, here and one more important word, we should know it here. Sometimes in medical examination, they are asking, the question is, what is the group number of the lanthanides and what is the group number of the actinides? Here, observe it here, group number 3rd B, 3rd B. Here actually in the main body, you are observe it here, first B group elements are here, second B group elements are here, third B group elements are here, third B group elements are here. The lanthanides and actinides both are present only in the same group, that is 3rd B group only. So after the knowing of the differences between the lanthanides and actinides, and here we should know the important properties of block elements or inner transition elements. These are also called as block elements, also called as inner transition elements, because their n-2 into f orbitals are partially filled with the electrons. Because of that reason, they are also known as inner transition elements here. Really, you believe it or not, many of the students who are reading the intermediate, they are getting the confusion writing up the electronic configuration of block elements when the student is observing this concept without by hearting. We can write the electronic configuration of block elements. Here the block elements electronic configuration is very important one, because many times they are asking even in IIT mains and entrance examination also. Therefore, observe it here. This is the structure of an atom of the block element. It is a nucleus. It is a valence shell. This is valence shell. This is penultimate shell. You know very well. The last orbit is represented by N. The orbit which is present before the valency orbit, it is represented by n minus 1, and before of that shell n minus 2. Here d orbitals are available, therefore n minus 1 into d. Here f orbitals are available, therefore n minus 2 into f. So in case of ୱାvelock elements, the differentiating electron is entering into the, not into the valency shell, that are entering into the antipenultimate shell. This is antipenultimate shell. The first one is, it is a valency shell, remember. Valency electrons means the electrons which are present in the outermost orbit. Penultimate shell means this is the penultimate shell, before the valency shell. Antipenultimate shell, these three shells are absolutely important in any competitive examination point of view. I think here, in case of ୱାvelock elements, the differentiating electron is entering into the n minus 2 into f orbitals. We can accommodate 1 to 14 electrons because in the f sublevel there are 7 orbitals are there. 7, 1, 2, 3, 4, 5, 6, 7. I think in one orbital we can accommodate the 2 electrons. 7 into 2, totally 14 electrons. Therefore, we are writing n minus 2 into f 1 to 14. Here, just by observing this one, you can write without by-hatting the electron configuration. That means, here you observe please, n_s2. The outermost orbit is completely filled with the 2 electrons in the s sublevel, whereas in the penultimate shell, in the n minus 1 into d, that is filled with the 1 or 2, sometimes no electrons in the d orbitals. But when you are taking the n minus 2 into f, we can accommodate 1 to 14 electrons. That's why by saying this electron configuration, simply we can write it here. Electron configuration of the ୱାvelock elements is very easy. n_s2, next one n minus 1 into d, next one n minus 2 into f, 1 to 14. Here 0 or 1 or 2. This is the valency electronic configuration of ୱାvelock elements. I think here, are you by-hatting here? Nothing. Without by-hatting, just by observing of the structure of the atom of the ୱାvelock elements, we can write it. That is, then s2 n minus 1 into d, 0 or 1 or 2. Sometimes 1 or 2 electrons are present in the d orbital. Here 1 to 14. Therefore, this is the outermost, a general electronic configuration of the ୱାvelock elements. But here, sometimes in some competitive examinations, they are not asking the directly general electronic configuration. They are asking the general electronic configuration of the lanthanides or actinides. This can be written as like this very easily based on this concept only. That is, here xenon for the lanthanides, you can write it here, xenon 54, 4f 1 to 14, 5d 0 or 1 and 6s2. This is the electron configuration of lanthanides. And to the actinides, xenon onwards, next element is radon, I think 86 and 54 atomic numbers, and 5f. If you know the writing of electronic configuration of the lanthanides, automatically we are able to write the electron configuration of the actinides also. Xenon, next element is radon, 5f 1 to 14, 6d, I think next shell 5d, next one is the 6d, 0 or 1 or 2 also here. 6s2, next one is I think here 7s2. I think, are you by-hatting here? Need not by-hat it here. Simply xenon 4f 1 to 14, because the differentiating electron is enters into the only 4f orbital, so that we can accommodate the electrons 1 to 14. Therefore, 4f 1 to 14 and 5d 0 or 1. Sometimes only one electron is present in the 5d, but whereas the last valency orbit is completely filled with the 2 electrons. Therefore, 6s2 you are writing. When you are writing the electron configuration of the lanthanides, automatically we are writing the electron configuration of the actinides also. So, if you are having the ability to write the electronic configuration of the lanthanides and actinides, even the properties of the important characteristic properties of inner transition elements we are knowing very easily. Need not by heart it here. Based on the electronic configuration, we are able, we can explain or we can understand it here. Even we can crack the any type of the questions which are giving the IIT entrance examination. Now, there are 5 important properties are there. The first important property is the oxidation number. Remember, oxidation numbers. Second one, formation of coordination complexes. Formation of coordination complexes. This is the second important characteristic property of inner transition elements. And third one is, you can take it here, that is magnetic properties. Magnetic properties. It is also almost similar to the transition elements. And next one is color properties. Color properties. And the last one is lanthanide contraction is the one of the most important concept in the inner transition elements. Lanthanide contraction. It is one of the important problems. Many times they are asking the questions regarding the concept of lanthanide contraction and its applications also. We can see them very clearly. First, you take the word of oxidation number. Whenever you are interested to learn about the oxidation numbers of inner transition elements, simply observe the electronic configurations. Here, the electronic configurations of inner transition elements, that are, I think, lanthanides are given, cerium to lutetium. See here, you can ask one question to me, that is regarding the lanthanum. Actually, lanthanum is not present in the A block. Lanthanum is not present in the A block, even though the rest of the elements are called as lanthanides, because all these elements are present after the lanthanum. These element properties are almost resembles to the lanthanum. Therefore, these are called as lanthanides. First, you observe the electron configuration, please. Look at the blackboard. Xenon, 4f0, 5d1, 6s2. Simple electronic configuration. I think here 4f0, 5d1. Whenever the differentiating electron is enters into the 5d1, naturally we can expect it here. That should be belonging to the D block only. It's not present in the A block. For the convenience only, we have written this electron configuration of the lanthanum in the lanthanides here. Now you can take it here. Next element is cerium. In the cerium, 4f2, 5d0, 6s2 and plus 6s2. This is the electron configuration. It means, remember, it means when the cerium is losing the 2 electrons from the 6s, naturally it is exhibiting the +2 oxidation number, +2. Sometimes when it loses the 2 electrons from the 6s as well as 2 electrons from the 4f orbitals, there will be a chance to exhibit +4 oxidation number also. So here, like this, you can observe it here, all these electronic configurations in the 5d0, 5d0, 5d0. Sometimes in case of gadolinium, you observe it here. Atomic number is 64. It is a previous given question regarding the electron configuration of the gadolinium in the IIT mains examination. So that please you concentrate here. Gadolinium, xenon, 4f7, 5d1. Before that element, you observe it here, 4f7, 5d0, 6s2. But next one should be electronic configuration 4f8. But off-filled electronic configuration is the stable one. I think in the F orbitals there are 7, in the F sublevel there are 7 orbitals are there. Therefore, we can accommodate the totally 14 electrons. Then that is a completely filled electron configuration. If the 7 electrons are there, that is off-filled electron configuration. Even in the off-filled and completely filled electron configuration, that are the very stable electron configuration. That is why that elements are trying to get the either the off-filled electron configuration or full-filled electron configuration. Though, so that here in case of gadolinium, here that electron, instead of joining up that electron in the 4f7, that will be entering into the 5d. Therefore, it is the abnormality is there in case of gadolinium 4f7, 5d1, 6s2. So that it loses only 3 electrons from the 6s, 1 electron from the 5d. As a result of that, it is exhibiting the +3 oxidation state. Normally, all these elements are exhibiting the +3 oxidation state. And next one, +2 oxidation state. Minimum oxidation number is, remember, minimum oxidation number +2, common oxidation number +3, maximum oxidation number +4. Remember, +2, they are losing the electrons, 2 electrons from the 6s in case of lanthanides, and when that elements are exhibiting the 3 electrons, 2 electrons from the s orbital and 1 electron from the either from d orbital or f orbital. Then you can ask the one question to me. But in case of f orbital, sometimes you can take it here, samarium, this element here. In case of this one, here also you are observing the +3. It means what? Why the only 1 electron is losing from the 4f? Only 1, actually here there are 6 electrons are there, even though it is losing the only 1 electron. Because the main reason is when it is in the aqueous solution state, the required quantity of hydration energy and lattice energy is available. So that we can remove, by using up that energy, we can remove the only 1 electron from the 4f sublevel. So thus normally these elements are exhibiting the +3 oxidation state. Maximum oxidation number is +4 oxidation. And these are the lanthanides, and if you are taking the actinides, +2 minimum, common oxidation number +3, maximum oxidation number +7. I think now so far we have seen very clearly that is about the oxidation numbers. Oxidation numbers normally minimum oxidation number they are exhibiting +2, common oxidation number +3, and maximum oxidation number +4 by the lanthanide, +7 by the actinides. And this is about the electronic configuration as well as oxidation number. To understand the oxidation number, definitely we should know the valency electronic configuration. In case of lutetium, you can observe it here. It's a abnormality electron configuration is there. Here 4f14 before that element, 4f14 5d0 is there. Next element lutetium here, xenon 4f14, the incoming electron is entering into the 5d1. Therefore, here the lutetium is exhibiting the +3 oxidation number by losing the 2 electron from 6s and 1 electron from 5d. This is about the oxidation numbers and electron configuration of the inner transition elements. And you can take it here. After knowing of the oxidation number, next property is the formation of coordination complexes. Here, when the metal ion is reacting with the ligand, then the M, L, N plus or minus N, this is the coordination complex. Metal ion, these are the ligands. You know, the ligand means the molecule or ion which is having the ability to donate the one pair of the electron towards of the central metal cation. That is called as a ligand. Example, you can take it here. NES3 is a ligand. It is donating the electron pair towards of the metal ion. Therefore, it is a ligand. When they are donating the electron pairs, they are only called as ligands. Next one, Ligands also many types, monodentate, bidentate, tridentate, tetradentate, pentadentate, like this based on the donation of the electron pairs. If they are donating the only one pair of the electron towards subcentral metal cation, that is a monodentate. If they are donating the two pairs of the electrons, bidentates. For example, if you are taking the hydrazine, this is the hydrazine compound, it is donating the at the same time two pairs of electron towards of the central metal cation. Therefore, it is a bidentate ligand. Like this, we can give it different kinds of the definitions to the all kinds of the ligands. After this, here mainly you should know it here. In case of transition elements, the transition elements can form maximum number of coordination complexes, but whereas in case of coordination complexes of the black elements are very less. What is the reason why the maximum number of the coordination complexes are not forming by the inner transition elements? We should know it here. That is only the important one. I think in case of transition elements, n-2 into f orbital, these are the partially filled f orbitals. Here f orbitals in inner transition elements that are not providing the empty orbital towards of the ligand. When the metal ion is providing the empty orbitals towards of the ligand, then only there is a chance to the formation of coordination complexes. But here, very rarely, they are not providing easily empty f orbital towards of the ligands. Therefore, the number of formation of complexes are very less to the inner transition elements or F-block elements. And after the knowing of the coordination complexes, next property, important characteristic property of inner transition elements, that is magnetic property. When you know the magnetic properties of transition elements, you can apply that knowledge to the even inner transition elements. Here, the magnetic property is obtained to the ions of inner transition elements due to the two reasons. Number one, first one is spin of the electron, second one is orbital motion. These two are the responsible to get the magnetic property of ions of inner transition elements. Here these reasons are very important one. But inner transition elements exhibit two kinds of magnetic property, that is, first one is paramagnetic property and the second one is diamagnetic property. Normally in the transition elements, in the transition elements, when the ions contains unpaired electrons, they exhibit paramagnetic property. Paired electrons or no electrons, diamagnetic property. Here also almost in case of inner transition elements, the same thing, same knowledge can be applied to that one. But here, in case of paramagnetic nature means the compounds which are slightly attracted by the magnetic field, that are called as paramagnetic compounds, or that nature is called as paramagnetic nature. Here the paramagnetic nature increases. With the number of unpaired electrons. If the number of unpaired electrons are increasing, the paramagnetic nature is also increases. If the paramagnetic nature is increases, their magnetic momentum 𝜇B value, their magnetic momentum is also increasing, that is represented by 𝜇B. 𝜇B is equal to, calculate the magnetic momentum of the ions of the inner transition elements. Here 𝜇L plus 𝜇S. 𝜇L means orbital magnetic moment, 𝜇S means spin magnetic moment. To calculate the orbital magnetic moment under root of L into L plus 1. To calculate the spin magnetic moment mu s is equal to under root of 4s into s plus 1. These two are useful to calculate the magnetic moment of spin and orbital. So when you add these two values, total magnetic momentum will come. Mu b is equal to mu L plus mu s. Therefore, mu b is equal to under root of L into L plus 1 plus under root of 4s into s plus 1. This is the equation to calculate the magnetic momentum. Just as I said you very clearly, if the number of unpaired electrons are increases, their magnetic momentum is also increasing. But here in case of gadolinium, it has 7 unpaired electrons. Even though its magnetic momentum is very less, sometimes in the competitive examinations they are asking. That is only because of the reason is mu L and mu s. That is spin magnetic moment and orbital magnetic moment. They works in opposite direction. They works in opposite direction. As a result of that, its original mu b value, its original magnetic momentum value is decreasing. Therefore, the gadolinium ion magnetic momentum is very less. And you can take it here. Example, the best example you can take it here by writing up the electron configuration of the cerium. You can observe it here. Cerium 58, xenon 4f2, 5d0, 6s2. When it is cerium is exhibiting the +2 oxidation number, you know, simply you can write it, loses the 2 electrons from the valency orbit, not from the inner orbit, because that inner orbit electrons are very much influenced by the nucleus. Therefore, it loses initially from the 6s, xenon and 4f2, 5d0, 6s0. There are 7 orbitals are there, 1, 2, 3, 4, 5, 3, 4, 5, 6, 7. Here n value is equal to. When the number of unpaired electrons are 2 in the +2 oxidation state of the cerium, it is exhibiting the paramagnetic property. It is exhibiting the paramagnetic property. Sometimes the maximum oxidation number of the cerium you can expect it here. Based on this ion, simply you can apply that knowledge to the even other elements or other ions also. When it is exhibiting the +4 oxidation number, you can understand it very clearly. Cerium, xenon, 4f0, 5d0 and 6s0. No question of having of any kinds of electrons in the 4f, 5d or 6s. Hence, here it doesn't exhibit the paramagnetic nature because of the no electrons. Only it is exhibiting the diamagnetic nature. If the paired electrons are there, diamagnetic. No electrons are there, diamagnetic nature. So this knowledge is useful to the even transition elements also. This is about the magnetic property of the inner transition elements. Mainly these 2 points are very important. These 2 points are the causes to get the magnetic property to the inner transition elements. A block మూలకాలలో ఒక ప్రత్యేకత కలిగి ఉన్నటువంటి the special property, that is the color property. Generally you cannot observe that kind of the property in the D block elements. That's why we should concentrate regarding the color property, because in many competitive examination they are asking the color property as well as magnetic, color and magnetic. These two are very important. But whereas in case of transition elements, the formation of coordination complex are very important one. That is a very, very important one. Here the color property of the transition elements can be explained based on the FF transition. FF transition. Try to understand please. DD transition is causes to get the color property to the transition elements. DD transition means changing of electron from one d orbital to the another d orbital. When the atom is absorbing the radiation, the electron is jumping from some d orbitals to another d orbital. Therefore, this is the DD transition. Where there is a DD transition, there will be color property. In the same way, where there is a FF transition, there is a color property. That means what? Simply based on the factor of FF transition means because of that reason itself only they are exhibiting the color property. Normally, you know, in the transition elements, where there is unpaired electron, there is a color property. Where there is a paired electron, there is no color property. They do not exhibit the color property. But here the special thing is there, that is here in the inner transition elements ions, sometimes they possesses, they contain, they are having unpaired electrons even though they are colorless. What is the reason? So regarding that questions only they are asked in the competitive examination in IIT mains and advanced level, so that you must concentrate regarding that one. Here first you can take it here, FF transition, this word is completed. Next one is when the no electrons in the f orbitals and 14 electrons in the f orbitals, they do not exhibit the color property. But sometimes when they contains a 1 electron or 7 electrons unpaired, here also when F13 is there, here number of unpaired electrons, here number of unpaired electrons 1, number of unpaired electrons 7, number of unpaired electrons 1, number of unpaired electrons 1. So here you can observe it here. When the one unpaired electron is there in a transition element, definitely that is exhibiting the color property. But even though here in case of the inner transition element, it has the one unpaired electron, even though it is not exhibiting the color property, that is due to the absorption of the IR radiation, infrared radiation, due to absorption of IR radiation by the inner transition elements. Therefore, that ion is not exhibiting the color property. Even you can take it a gadolinium plus 3. Here there are 7 unpaired electrons are there due to the absorption of the UV radiation. Gadolinium plus 3 ion is also colorless ion. Next, if you are taking the electron configuration of F13, there will be one unpaired electron is there. Where there is a one unpaired electron, here it is also not exhibiting the color property. This is the special thing in case of the color property of the block elements. And one more interesting property can be observed, but we can't see that kind of the property in the transition elements or D block elements. You can take it here, the lanthanides. In the lanthanides there are 14 metals are there. First starting element, you are taking the lanthanum here, middle element is the gadolinium, the last element is the lutetium. When normally, casually they are exhibiting the +3 oxidation number, no doubt at all, because they are losing the 2 electron from the outermost orbit and 1 electron from the either the d orbital or f orbital, you know, +3, +3, +3. Here when you are taking the lanthanum +3, here number of unpaired electrons are 0. In the lutetium +3, number of unpaired electrons are 0, therefore colorless. No doubt, this knowledge can be applied to the even transition elements also. No change. Next, the middle element is the gadolinium. The middle element is gadolinium. After the lanthanum, cerium is there. Whatever you are observing the colors from lanthanum to gadolinium, the same type of colors are exhibited by the ions which are from gadolinium to lutetium. The same type of colors. When the same number of unpaired electrons are there, Example, you can take it here. After the lanthanum, cerium is there. After the lutetium, ytterbium element is there. In the ytterbium, before the lutetium, ytterbium is there. In the +3 oxidation state, it has only one unpaired electron. Cerium +3, only one unpaired electron. When the one unpaired electrons are there, it is not exhibiting the color property. No color, no color. Just given very clearly. The reason for that one is the absorption of the infrared radiation. This is the very interesting thing. So that you can take the other ions. Other ions, whatever the, for example, a particular ion is exhibiting the green color. Here also this ion is also exhibiting the green color. If it is exhibiting the pink color, this ion is also exhibiting the pink color. This special type of property can be observed in the color property of block elements. That is why normally in the competitive examination they are asking regarding the questions of color property. So that please you must remember F0, F14, no unpaired electrons, no color, no doubts. F1, F7, F13, no color, but here if the number of unpaired electrons are 1, due to the absorption of IR radiation, no color. F7, due to the absorption of ultraviolet radiation, its energy is more because its wavelength is very less. You know, energy and wavelength inversely proportionality. If the wavelength is increases, energy is decreasing. You know that is. Even in case of F13, here only one unpaired electron is there. Therefore, here also due to the absorption of IR radiation, that is not exhibiting the color property. This is the color property of the block elements. And the next, the last important word is there, that is the lanthanide contraction. In the block elements or in the inner transition elements, and one of the important most property is also there, that is lanthanide contraction. Lanthanide sankochamu antaru. Lanthanide sankocham meeda సంకోచించక ఎన్నో రకాల ప్రశ్నలు అడుగుతున్నారు. ఒక్కసారి మీరు గమనించండి. సో దట్ యూ మస్ట్ కాన్సన్ట్రేట్ రిగార్డింగ్ ద కాన్సెప్ట్ ఆఫ్ ద lanthanide contraction. ఇట్స్ ఏ సమ్వాట్ డిఫికల్ట్ టు అండర్స్టాండ్ ద lanthanide contraction. కాబట్టి కొంచెం జాగ్రత్తగా అబ్జర్వ్ చేయడానికి ప్రయత్నించండి. Lanthanide contraction. What is the lanthanide contraction? First, to understand the lanthanide contraction, lanthanide contraction is only due to the poor shielding effect of the f orbitals. Remember, poor shielding effect of the 4f orbitals. Due to that reason itself only lanthanide contraction is taking place. Here try to understand. If you are taking the f, or say it is an atom, it is the f orbital. When the f orbital is like this, here the attraction of the electron towards of the nucleus is very less because it is acting like a screen. It is acting like a screen. ఒక తెర మాదిరిగా అడ్డుగా వచ్చేస్తుంది when the size is like this. But due to the diffusion of the f orbital, it is due to the diffusion of the f orbital. చూడండి, f orbital యొక్క షేప్ ఈ విధంగా మారింది when it is changing into the like this. When it is changing like this, then attraction of the valence electron towards of the nucleus is increasing. Attraction of the valence electron towards of the nucleus is increasing because the shielding effect is decreasing. ఒక అడ్డు తెరగా వచ్చేది తగ్గిపోతున్నది కాబట్టి ఈ ఎలక్ట్రాన్ కేంద్రకం వైపు ఎక్కువగా ఆకర్షింపబడుతుంది. సో డ్యూ టు ద పూర్ షీల్డింగ్ ఎఫెక్ట్ ఆఫ్ ద f orbitals, that is only the main reason is diffusion of the f orbital, the electron is attracting towards of the nucleus. So that is why from lanthanum to lutetium in the +3 oxidation number state, gradually the ionic size is decreasing. Slowly, gradually, ionic size is decreasing from lanthanum to lutetium. The decreasing of ionic size from lanthanum to lutetium is called as lanthanide contraction. Danne lanthanide sankochamu antaru. Due to the lanthanide contraction, what are the main consequences that are very, very important? There are three important consequences are there. ఈ లాంథనైడ్ సంకోచం వల్ల మూడు రకాల ప్రభావాలు ఉంటున్నాయి. ద నెంబర్ వన్, ఫస్ట్ యూ కెన్ టేక్ ఇట్ ద basic nature of the hydroxides. You know basic nature of the hydroxide. If it is lanthanum hydroxide, when it is exhibiting the +3 oxidation number, lanthanum +3 OH minus. Therefore, LaOH taken 3, lanthanum hydroxide. It's a basic compound because it is releases the OH minus ions when it is dissolved in the water. From lanthanum to lutetium, try to understand, gradually the size is decreasing. Gradually the size is decreasing. When the size is decreases, the metallic nature is also decreasing. Remember, the metallic nature is also decreasing. When the metallic nature is decreases, non-metallic nature is increasing. It means when the metallic nature is increases, metallic nature directly proportional to basic nature of the hydroxides or oxides of the metals. For example, you can take it here, lithium oxide, sodium oxide, potassium oxide. As we move down the group, metallic nature is increasing. When the metallic nature is increases, their basic nature is also increasing. Therefore, potassium oxide is more basic than the sodium oxide and lithium oxide. This is the order of the basic nature. In the same way, metallic nature is decreasing from left to right. When the metallic nature is decreases, automatically the basic nature of hydroxides is also decreasing. That is only due to the lanthanide contraction. The basic nature is decreasing. That can be explained even based on the bond strength also. As we move from lanthanum to lutetium, the bond strength is increasing between the metal and OH group. Therefore, when the bond strength is increases, it is not losing the easily OH minus ions. When the number of OH minus ions are more, when it is dissolved in the water, its basic nature is more. So that simply, blindly, you can remember from left to right, the basic nature is decreasing. That is only due to the lanthanide contraction. And now come to the same knowledge you can apply it here. That is solubility of the salts. లవణాల యొక్క ద్రావణీయత, నీటిలో కరిగే ద్రావణీయత కూడా తగ్గుతూ ఉంటుంది. The solubility of the salt is decreasing from lanthanum to lutetium because metallic nature is decreasing. When the metallic nature is decreases, automatically the formation of the salt nature is also decreasing. Therefore, when they are dissolving in the water, if the metallic nature is more, the formation of the salt nature is also more and it is soluble easily in the water. But as we move from left to right, here the solubility of the salt is decreases. Only this is also due to the lanthanide contraction. And the last one is the extraction of the metals. Now you can take the block elements. Many of the block elements are occurred. They are present only in the one kind of a mineral or ore, that is due to the lanthanide contraction. Therefore, it's a very difficult to separate the metals from the monazite ore, because in the monazite ore there are many kinds of block metals are present because of almost equal size is there. Therefore, it's a very difficult to isolate that elements from the monazite ore. These three are the very important. These are the consequences. Basic nature decreases, solubility of the salts decreases, and it's a very difficult to separate the metals from the monazite ore. These are the main important postulates of inner transition elements. Dear friends, based on the previous knowledge of block elements, you are able to crack any kind of questions, the questions which are given in any competitive examination, so that you must concentrate regarding the concepts of block elements. The two only mainly concentrate on magnetic properties. Once again I am repeating. And the second one is color properties, and third one coordination complexes are not important in the inner transition elements. Color, magnetic and lanthanide contraction. You can observe it here. Previous questions, some of the exam questions I am taking here, you can observe it here. The first question is given, the outer electronic configuration of gadolinium is, you know, already you have observed very clearly the electronic configuration of gadolinium. Gadolinium is the center element of the 4F series of the block elements. Therefore, you can observe it here, 4F8 5D0 6S2, first option, 4F4 5D4 6S2, second option, third option is 4F7 5D1 6S2. I think already we have seen very clearly in case of the gadolinium, the differentiating electron is not entering into the f orbitals, that is enters into the 5D1. So to get the stability purpose itself only. Therefore, 4F7 5D1 6S2 is the correct electron configuration of the gadolinium. Many times they are asking only gadolinium electron configuration because of abnormality. దానిలో భిన్నమైనటువంటి ఎలక్ట్రాన్ విన్యాసం కనపడుతుంది కాబట్టి దీన్ని సాధారణంగా ఈ క్వశ్చన్ ఎగ్జామినేషన్లో ఇస్తున్నారు. కాబట్టి మీరు ఎక్కువ కాన్సన్ట్రేట్ చేయడానికి కోసం ప్రయత్నం చేయండి. ఎందుకంటే వాస్తవానికి 4F8 5D0గా ఉండాలి, కానీ 4F8 5D0గా ఉండకుండా ఆ వచ్చి చేరే ఎలక్ట్రాన్ 5D లోపలికి చేరటం వల్ల అలా మారుతుంది. కాబట్టి ఇట్స్ ఏ అబ్నార్మల్ ఎలక్ట్రాన్ కాన్ఫిగరేషన్. Therefore, the answer is third one to the first question. And see one thing, when you are observing this question, whenever the candidate who is going to write that competitive examination, when they know all the concepts, when they are understanding all the important aspects which are present in the transition elements as well as inner transition elements, then only we are able to crack the questions which are given in the competitive examination. The best example you can take it here, that is in the context of the lanthanides, which of the following is not correct. Try to understand. The questions are giving two types of questions, that are positive question and the next one is negative question. Positive question, it's not a positive question, it's a negative question, because in the question not correct statement is asking. First one, all the members of elements exhibits +3 oxidation state. You know, already we have seen very clearly the lanthanides and even actinides also normally they are exhibiting the +3 oxidation state. That is a correct statement. And but he is asking not correct statement. Try to understand. అడుగుతున్నటువంటిది సరి అయిన వాక్యము కానిదేది అని అడుగుతున్నాడు. కాబట్టి దాన్ని పరిశీలనాత్మకంగా చూడండి. ఇక్కడ చాలామంది తప్పు పెడుతున్నారు. నాట్ కరెక్ట్ కాకుండా కరెక్ట్ అనేది తీసుకున్నట్లయితే ఆన్సర్ వేరే అవుతుంది, నాట్ కరెక్ట్ అయినప్పుడు ఆన్సర్ వేరే అవుతున్నది. కాబట్టి క్వశ్చన్ పాజిటివ్లో ఉందా నెగిటివ్లో ఉందా అబ్జర్వ్ చేయండి. బికాస్ ఆఫ్ సిమిలర్ ప్రాపర్టీస్ ద సపరేషన్ ఈస్ నాట్ ఈజీ. మీకు తెలుసు లాంథనైడ్ కాంట్రాక్షన్తోని సిమిలర్ ప్రాపర్టీ ఉండటం వల్ల, సిమిలర్ అటామిక్ సైజ్ ఉండటం వల్ల ఇట్స్ వెరీ డిఫికల్ట్ టు సపరేట్ దట్ ఎలిమెంట్. సో దట్ ఈవెన్ ద సెకండ్ స్టేట్మెంట్ ఈజ్ ఆల్సో కరెక్ట్ వన్, even the second statement. And third one you can take it here, the third statement, availability of 4F electrons result in the formation of compounds +4 state for all the members of the series. Actually this is not correct one. You observe it here based on the all the concepts which are given in the black elements. This is not a correct statement. Therefore, regarding this question, the answer is the third one. You can observe the fourth one. There is a gradual decrease. It's a symbol to the decrease. There is a gradual decrease in the radii of the members with the increased atomic numbers in the series. As we move from left to right due to the lanthanide contraction, ionic sizes, their sizes are decreasing, you know, therefore it is a correct statement. Out of 4 statements, the third statement is wrong statement. So thus the answer is the third one is correct. And come to the next question. It's also EAPCET 2000 question, 2007 I think. Here identify the incorrect statement among the following. Here also negative question second time is repeating here. Many times they are asking the negative questions. So that when you are writing the examination, you observe it whether it is a positive question or negative question. There itself only they are doing the mistake. And first you observe the statements which are given in this question. Deep black elements show irregular and erratic chemical properties among themselves. And second one, lanthanum and lutetium have partially filled d orbitals and no other partially filled orbitals. Next, the chemistry of various lanthanides is very similar. Next one is 4f and 5f orbitals are equally shielded. One thing remember, in the shielding effect, in the lanthanides, the poor shielding effect is due to the 4f orbitals. In the actinides contraction, that is poor shielding effect of the 5f orbital. There is some difference is there, but in the last statement you observe it here, 4f and 5f orbitals are equally shielded. It's not a correct statement. Therefore, according to this question, identify the incorrect statement among the following. You observe first 3 statements are the correct one according to all the concepts, and the last one is incorrect statement. So that answer is the fourth one.